will be, studying how to, what are the major steps of the to formulate a model from a scenario, and then we will be doing some examples of formulating it, and then we will go to the graphical method. Do you hear me? Okay. So let's start with the 5 steps of the modeling. So the very uh, when we have a problem, a real time problem, we have to do it in 5 phases. There are 5 phases of the operations research that tackles the problem. The very first phase is the definition of the problem. You have to uh, yes, I will. Okay, so there are 5 phases of tackling for problems. So whenever there is a scenario of manufacturing or service given to us, we need to solve it using the 5 major steps. The very first step is to define the problem. Define the problem. In this problem definition, we need to take like, yes, can you see it now? How to tackle the OR problems. There are 5 phases or 5 steps to to tackle the OR problems. Whenever there is a scenario, I will write like okay, I will write like in more. Okay, 5 steps of solving OR problems. The very first step is definition of problem. Can you see it? So in definition of the problem, this is the very first step. And in this, we discuss the scope of the problem, which is under investigation. And we identify the basic elements of the problem. For example, we are given a scenario of some manufacturing, okay? And we have like some products. Now in the problem definition, you have to see like, what is the scope of the problem? How many products are given? And what is the cost or profit per unit piece or per unit product? For example, if it is given like, 3 products, as I, explained it yesterday, for example, mobile phone, tablets, and laptops. So in the problem definition, you need to see how many variables are there, how many, elements are there. Laptop is first element, the mobile phone is second element, and tablets is the third element. So in the problem definition, you need to see what is the scope, how many things are given, and what we have to find out in the study. So this is the first phase of the or problem solving. The definition of problem is the first step, and in this we identify 2 things. First is the scope, what things are given to us and what we need to find out. And the second is the identify the basic elements of the problem. For example, we are given like how many products are given, what are the constraints of it, what are the limitations, and what are the the study about, what is the system about. Is it a manufacturing, is it a service, and how many limitations or constraints are there. I will explain it when I uh, do a practical uh, representation of this uh, 5 steps. So I will explain each step, and then you will understand it if there's problem. But this is just just to let you know that we have to do it in 5 basic steps. The second one is model construction. This is the very important, most important part is model construction. You need to learn this art. If you learn the art of model construction, you can do anything in operations research. If you have model, you can just put it in a software or anything like that, and you can have the solution of the problem. So model construction is basically defining the 3 basic things: the objective function, first thing, objective function. The second thing is the constraints of it. What are the limitations? And the third one is defining the decision variables. These decision variables will come from the definition of the problem. When we define the problem, the decision variable will come out of it. Like just I said, like we have 3 products. So the decision variable comes from the definition of the problem. When we study the scope of it, we have 3 products. It means that the decision variable will be 3. Okay. So now move on to the third phase of it. After we define the problem and construct the model, the mathematical model of it, you need to do the model solution. Model solution. You have to solve the model which is constructed earlier. Now we can do it by 2 ways or 3 ways. Okay. The first method is graphical method. Graphical method is used when we have only 2 variables. When we have 2 decision variables only, then graphical method is used. If there are more than 2 decision variables, then we will use simplex method. And the third thing is using software packages. Here comes the Torah. So the model solution is done by using 3 main methods. The first thing is graphical method, and graphical method is utilized when we have only 2 decision variables, like only we have 2 products that we want to compare, and we want to find the quantities that are best suited for the manufacturing setup or the service setup. And if the decision variables are 3 or more than 3, then we use the simplex method. And the third one is using some software packages. And these software packages also utilize the same simplex, but it is, automated. You just don't have to do it using hand. Okay. So moving on to the fourth step of the solving our problems. So the fourth step is the model validity, model validation. So the model validation is actually used to check whether the proposed model either it is complying to the purpose or it is not compliant to the purpose. Like the solution that we found or the model that we made, is it representing the actual scenario or no, or not? Contradicting at some it's in some ways, or at some point it is contradicting that. So you have to validate it. The model validation is done by several methods, and it is done using the results of it. For example, in the results we put some values, and we see that either it is complying or it is not complying. And then the fifth phase is the implementation of the solution. We just implement what we solved the model for, and we see that either it is useful or we need to improve the solution. These are the 5 phases of solving our problems. The first thing is definition of the problem. In definition of the problem, we use 2 things: the scope of it, like what is given and what does it want from us, and then identify the basic elements of it. The basic elements are actually the decision variables of it, and it will come from the defining the problem. The second phase is the model construction. This is the most important part of it. But if you can define the problem, you cannot construct a model. So you have to look for things in the definition and then put it into the model construction phase. In the model construction, we have three things: objective function, constraints, and decision variables. All of these things, it will come from the problem definition, but you have to put it into a certain way and then solve it. The third thing is the model solution. The model solution can be done into like three main ways: the graphical one, the simplex, and software packages. Graphical method is a method that is used when we have only two kind of variables. If we have more than two variables, then we go to simplex method. It is a more detailed way, and in this method can accommodate more than 10 and hundreds of variables. And when the variables are more than like 20 or 15 or maybe more, then we use the software packages. It actually uses the same method, but it is automated, so you don't have to bother about the uh, solving it like in detail. It will just give you solutions, and in minutes. You don't have to waste like hours to solve a simplex method problem using like 10 variables or 15 variables, because it is very lengthy. You have to take hours. Then comes the model validity. The model validity just it is a concern that if the model is actually presenting the scenario, are the results viable or not, and if the results are found viable, then we implement it, and we see that either the solution is useful, or we have to improve the solution more and go towards the more optimistic way. Okay, so now I will define uh, a mathematical model out of a physical scenario, and I will show you these five phases of it into solving that problem. During the solution, I will explain all these five phases, and then we will go towards the uh, graphical method. Let me pick uh, a problem from the book, and then we can. Should I do the ready mix model that is given in the book? Or I'm using same book that you refer to, the Hamdi Taha. Yeah, so I will do an example from it, and then so it is the most followed book by the professors and instructors. Most probably your exam question will also come from this book, or maybe it is self-made, but it will follow the same principle of the Taha book. So it will be good if you follow this book. So okay, so here we have raw materials of two types. One is M1 and the other one is M2. Okay, and both of these are used to produce two kind of pants. One is the exterior pant and one is the interior pant. And then we have the limitation, which is daily availability. Let me switch to laptop, and I can share the screen of the book, and then I can I will write uh, using my mouse, like to just represent what the constraints are and what are the decision variables. Or just should I use paper? But using mouse, I can write like very good. Paper is okay. Okay, if paper is good, then that is. I am also yes, yes. That is okay. It is already defined, so I will just it will take like four. Okay, it is like page 45. I'm writing over here. Okay, P45. Okay, so we have two kinds of raw materials, M1 and M2, and we have two decision variables: the quantity of the exterior paint and the quantity of the interior paint. And we have constraints of daily availability of this raw materials. One is available like 24 tons daily, and the other one is available like 6 tons per day. The amount that is used, it is used 6 tons of M1 in exterior paint and 4 tons of it in interior paint. M2 is used 1 ton in exterior paint and 2 tons in interior paints. Okay, and now the profit per ton in thousands is 5 for the exterior paint and $4,000 for the interior paint per ton. This is the problem given. This is actually already a defined problem. This is not something like we defined it from some uh, paragraph or anything like that, like some explanation. It is already a defined problem. We will define problem like this from some given scenario. So this is already defined, but still I have I will identify the sections of it so that you understand, and I will then make a model out of it. So the first thing is the definition of the problem. Now, what is the scope of it? Scope. The scope of it is to define quantity of exterior and interior paints to be manufactured to optimize profits. This is the scope of this problem. What we have to do, we have to do, all we have to do is to define the quantities of the exterior and the interior paint in this scenario under these limitations, under these two limitations of raw materials, okay, to optimize the profits. And the profits per ton are given for both the exterior and the interior paints. You understand? Okay. So now this is the first phase of it. You know, you just have to look for things like what we'll have to do and what things we have to solve the problem. This is just defining the problem and checking the scope of it. Now we will go to the model construction. This is the most important thing. You will be given problem like this, or you will be given a scenario in kind of paragraph form, and you will have to extract the information, put into a table like this, and then define the model out of it. Or sometime you may be given a table like this, and you have to make the model and solve it. Okay. So the model construction. Now in the model we have three things. We have objective function, constraints, and decision variables. So first, from the definition of the problem, what are the decision variables that we are studying here? Can you tell me what are the decision variables? I'm just engaging you, like, to be with me and think about things here. No, not the raw materials. What we are inspecting this problem for? What we need to find? We need to find the quantity of the exterior paint. No, profits are given. These are the profits. Profits are given to us. We don't need to investigate the profits. We need to investigate the quantities of the exterior paint and the interior paints. The problem is all about defining the quantities of the exterior and the interior paint. So the decision variable are two variables. Two variables. You can define it as x1 and x2. So x1 will represent the quantity of exterior paint, and x2 will represent quantity of interior paint. So these two are the decision variables. We have to solve the problem for finding these two quantities that maximizes the profit. Now you understand? Yes, okay. Now we have decision variables. The first thing that we do is whether it is a maximization problem or minimization problem. So here the profit per ton is given. So this is maximization problem. Very good. So we will set the objective function first. And objective function is maximize z is equal to the profit is given for each. So we will multiply the profit using the sum product thing. 5 into x1 plus 4 into x2, because x1 is yielding 5 $1,000 per ton, and X2 is yielding $4,000 per ton. Okay. Now we will use subject to. Now we will define the constraints of it. Now you see there are two raw materials given. So the constraints are also two. Now what will be the first constraint? The first constraint is the raw material used in exterior paint and interior paint, raw material M1. So we use 6 tons of raw material in X1 and 4 tons of raw material in X2. And the total availability is 24 tons per day. So the total amount to be used daily, it should be less than 24 tons. So this is our limitation. The second constraint will be 1 into X1. Because it is the maximum available. Maximum available is 24. If it were given like this is the minimum available, this is the maximum daily availability. So we will use lesser than that. If it were given like the minimum quantity per day, so we will use we can use greater than that. Okay, then we use the greater than or equal to 24 if it were given that these are the minimum quantities that are available daily. You got it? Now for the M2, this is the constraint for M1. And now for the raw material M2, we use 1 ton of raw material in X1 and 2 tons of raw material M2 in X2. And the daily available is 6 tons. So it will also be less than or equal to 6. Got it? And the third constraint that is universal will be non-negativity, that X1 and X2 must be greater than or equal to 0. It means that you need to produce something. You cannot, have the solution that you don't produce anything and not be in, have zero profit. Yes, so this is the non-negativity constraint. And it will be you have to put it for all the problems. For all the problems, you need to put the last constraint. This is very important constraint. You cannot, left it, in any problem. You have to put it, the non-negativity. Okay, now the third phase is to solve the model. Now, what method will we use to solve this model? Considering we have two variables. So what method will we use? Yes, the graphical method. So the graphical, yes, so we will go for the graphical method to solve the problem. Now, to solve using the graphical method, I will jump to graphical method. So today we will cover graphical method also. Okay. So now jumping to the graphical method. You understand how to define the problem and then construct the model out of it. Inshallah, in the next examples, I will try to bring some problem that are paragraphed, that are not in tabular form, that are paragraphed. So you just know how to extract information and make the model and then solve it. So we will practice those kind of problems also. To make a graph with the XY plane. So I will make a graph for it. This is the X1 and this is the X2. This is the X1 variable and this is the X2 variable. You can use it interchangeably, that's not an issue. Okay. Now we have the objective function as 4x2 and the subject to 6x1 plus 4x2 less than or equal to 24, x1 plus 2x2 less than or equal to 6, and x1 2 greater than or equal to 0. So now we will solve the first constraint and second constraint to find the values of x1, x2 that we need to put in the objective function and find the optimal profit for this company. So first of all, taking constraint 1, 6x1 plus 4x2 less than or equal to 24. We have here inequality sign. First of all, we will have to equate it. We will remove the inequality sign and we will equate it. Okay. Now in the equation, we will put x1 is equal to 0 and we will find what is x2 when x1 is equal to 0. Now 6 into 0 plus 4x2 is equal to 24. We will get 4x2 is equal to 24. So dividing both sides by 4, we get x2 is equal to 6. So the first point that we get here is at x1 is equal to 0, x2 is equal to 6. So here x1 is equal to 0, but x2 is equal to 6. So we will do it like this way: 2, 4, 6, 8, 10. We will graduate it. And here also 2, 4, 6, 8, 10, 12, and so on. Okay. So now we will plot this point into the graph. Okay. So at x1 is equal to 0, x2 is equal to 6. So this is these two are the points. x2 is equal to so we need to put yes. It was disconnected. So did you understand what I said or nah? You skipped it. Okay. We have the objective function, this one, 5x1 plus 4x2. And we have this whole, mathematical model. We will take the first constraint, which 6x1 plus 4x2 is less than or equal to 24. And we will transform the inequality sign into equality. You see here, 6x1 plus 4x2 is equal to 24. I just converted it into equality sign. After that, we will put x1 is equal to x1. We will put the value of x1 0, and we will find out what is x2 at this point. So if you put x1 is equal to 0, then the x2 is equal to 6. It comes the value of x2 for x1 is equal to 0. Similarly, at x2 is equal to 0, we need to find the value of the x1 in the first constraint. Okay, so now putting the value of x2 is equal to 0 in constraint 1, we see that 6x1 plus 4x2 is equal to 24. Now putting the value of x2 is equal to 0, we get 6x1 plus 4 into 0 is equal to 24. We will get 6x1 is equal to 24. x1 is equal to 24 over 6, which is equal to 4. So at x2 is equal to 0, x1 is equal to 4. Now going to the graph again, we will plot this value. x2 is equal to 0, x1 is equal to 4. Now x2 is equal to 0 is here, is lying here. Okay, this is 0, 0. Okay, so now at x2 is equal to 0, x1 is equal to 4. So this is the point. Okay, now we will connect these 2 points. We will just connect these 2 points. So this is the constraint 1, C1. Now here is a trick. You need to, kind of be focused here. This is, we know that it is less than or equal to 24. We see here. You see it? That the constraint is 6x1 plus 4x2 less than 24. So this, the direction of it will be towards the origin. And what does this direction shows? This direction shows that the feasible solution is lying beneath this line towards this direction, not in this direction. So this area is gray area. The feasible solution is somewhat over here. Any point in this plane is feasible solution. And beyond this line, every point is non-feasible solution. It will not satisfy the constraint. You see? For example, I take x2 is equal to, for example, 8. If I take x2 is equal to 8, it is lying here. x2, 8 is lying here. So where is it? It is above the line. So it will not satisfy the constraint. So x2 cannot be equal to 8. You understand it? Now we will come towards the second constraint. Yes. It is it shows the direction of it, whether it will be towards the. So here it is towards the origin. So the line that we draw between 4 and 6, the solution cannot be greater than that. It cannot be greater than 6 for x2, and it cannot be greater than 4 for x1. because it is going beyond this line. And everything that goes beyond that line, it is infeasible. That is not feasible. Okay. In similar fashion, now we will uh, solve the second constraint and then find the solution for the problem. We will have the values of x1 and x2 that gives the optimal solution. That will give the maximum profit. And on that note, I will show you that how many possible feasible solutions are there and how many are there infeasible, and which one is the most optimal one. Okay. Now taking the second constraint. The second constraint is x1 plus 2x2 is less than or equal to 6. So first of all, we will have to, what we will have to do here? Yes, we will have to equate it. Just to have some specific solutions. Because in inequality, we cannot have, we will have approximations. Now, for at x1 is equal to 0, we need to find the value of x2. You see? Now, putting x1 is equal to 0 in the equation, we see that 0 plus 2 into x2 is equal to 6, which gives us x2 is equal to 6 by 2, which is equal to 3. So x2 is equal to 3 for x1 is equal to 0. If you put x1 is equal to 0, x2 is going to be 3. Now, similarly, for x2 is equal to 0, we need to find the value of x1. Now, putting x2 is equal to 0 in the equation, we see that 2 into 0 is equal to 6. So x1 is equal to 6. Now we have 2 points here. For x1 is equal to 0, x2 is getting 3 value, and for x2 is equal to 0, it is getting 6 value. So this point and this point need to be plotted in this plan, XY plan. Okay, for x1 is equal to 0, it will lie over here. x2 is equal to 3. 3 will lie somewhere here. So this is the line. Okay. Now, for x2 is equal to 0, x1 is equal to 6. So we will connect these two lines. Now, the area of the feasible solution is this. This is the area of the feasible solution. Now, the feasible solutions are what are the feasible solutions over here? The first solution is 0, 0. Means producing nothing. Okay. The second feasible solution is 0 and 3. When we make 0 tons of exterior band and 3 tons of interior band. Okay. The third solution is 4 and 0. Means we need to make 4 tons of exterior band and 0 tons of the interior bands. And the optimal solution is where these two lines cross. This is the optimal solution. So if we had like a graphical paper, we can, easily trace out this problem. But I guess according to my approximation, this point is somewhat 3, 2. It means 3 tons of X1 exterior band and 2 tons of interior band. So the other solution is 3 and 2. Now we will check all of these 4 solutions, solution 1, 2, 3, and 4, using this objective function. Yes, yes. It can have more than 4 points. Like, no, it depends on the number of constraints. Like we have 2 constraints over here. So we have 2 lines crossing each other. If there are 3 constraints over here, then it will have three lines crossing each other. So we can have like 6 or 7 points maybe. Yeah, so it depends on the number of constraints. If the number of constraints are 2, so it will most probably have like 4 solutions, 4 points. If there are 3, it will, at most it will have like 6 points. But it can have like more, even if the number of constraints are like 4 or 5, then it can have like even like 9, 10, 11 points. Depends on how many points they are crossing each other. You see that? Now we will use these 4 solutions and we will identify which one is the best solution, which one is feasible, and how many infeasible solutions are there. So for the infeasible solutions, any point that is lying in this plane, in this plane, in this plane, and in this plane, they are going to be infeasible solution. For example, if I take x2 is equal to 4, it is infeasible solution, because our feasible solution is like not beyond the 3, because beyond the 3, it will contradict the second constraint. So it should obey all the constraints, not just one, but all the constraints. If it is not obeying any constraint, anyone, then it is infeasible solution. Okay. So now we will check these 4 points and we will see which one is the optimal solution and which one are the feasible solution. First of all, checking x1 is equal to 0, x2 is equal to 0. For this, we will get like the maximum z is equal to 5 into 0 plus 4 into 0, which is equal to 0. So we will get 0 profit, which is still feasible. It is feasible, but it is not optimal. You can have it, but it is not the maximum that you can have. Now for the second one, we have maximum z is equal to 5 into 0 plus 4 into 3. So it will give us $12,000. For the third one, it will give us maximum z is equal to 5 into 4 plus 4 into 0. It is giving us $20,000. For the fourth one, it is giving us 5 into 3 plus 4 into 2, which is giving us like 15 plus 8, $23,000. So which one is the maximum one? This one. And it is achieved using Yes, it is achieved using x1 is equal to 3 terms and x2 is equal to 2 terms. So this one is the optimal solution. All others are feasible. You can have it, like you can have $12,000 of profit, but it is not the maximum that you can achieve under these circumstances. You can have $20,000 as a profit, but it is not the maximum that you can achieve under the circumstances. 23,000 is the maximum you can achieve. So this is the optimal solution. You understand the ready mix problem now? Okay. Let me grab some more papers because I'm scarce of papers over here so that I can solve some other problems and we can move on to the graphical problems. I will solve like two more problems on this graphical method, and then in the next lecture, we can move on to the simplex, and we will use both methods by hand on paper, and then I will show you a tutorial of Torah, how to use Torah, and implement it over there, and we will compare both the results. It will be same. Okay. Let me grab some papers, please. You need to give me like maybe 2, 3 minutes or 4 minutes. Okay. Okay. So I'm back with some papers. Okay. So now moving on to some other problem, on the graphical method. Okay. Okay. Yes, yes. Hello. Yes, I'm looking for some question, that is related to. Yes, I'm looking for some question that is related to the graphical method so that I can solve it, Yes, yes. So here is a question like uh, we have like two raw materials A and B, and there is a requirement for but it is going for a three products. So we will have like three. Okay, so we have a problem that is have the raw material. Two kinds of raw material are used in the production. We have like two products, hi-fi 1 and hi-fi 2. Okay, A is using 2 while B is using 3, 4, 2, and the maximum capacity or availability it is available like 4,000, and this is available 6,000 units per day, and the profit per unit is 30 and $20 respectively. Now we will solve this problem using the graphical method. It is like in similar fashion. Okay, so now we have two variables. The first one is hi-fi 1, so we will represent it using x1, and the hi-fi 2 we will represent it using x2 variables. Okay, and we have two raw materials. So this is the constraint 1, and this is the constraint 2, C2. Okay, and this we will use in the objective function. We will make objective function out of this profits. So the objective function will be maximum z 30 into x1 plus 20x2. Subject to suppose subject to no, I got it from another book. I will text you send that book to Josefa and you can see the I will share the screenshot of it, the problems. Yes. So now you need to support me in this, to so that I can understand that you now fully, understand it. Can you? Yes, please. You should because I want to know that how much percentage you got it. So for it. So the first constraint will be yes the 2x1 plus it will be 3 into x2 and it will be less than because it is the maximum availability and it will be less than or equal to 4,000. Now the constraint 2, that is the raw material B, it will be like 4x1 plus 2x2, and it is maximum, so we will be use less than or equal to. Now we will solve it. So for the solution, first of all, you need to draw an xy plan. This is vx1 and this is x2. Okay. So now we will first take the constant one and make it inequality. Then we will put x1 is equal to 0 and we will see that what the x2 value. So the x2 value will be somewhat 1300. $1,333. Okay. Now for x2 is equal to 0, x1 will be 2000. You understand it, or I should do it like by step by step. I just skipped a few steps so that the calculation. Not 0 and 4000. If we put x1 is equal to 0, we will get x2 is equal to 4000 divided by 3, which gives us like 1333. And for x2 is equal to 0, we will get half of it, like x1 is equal to 2000, because 4000 will be divided by 2, so we get 2000. So for the constant one, we have 2 points. First one is x1 is equal to 0 and x2 is equal to 1333. And for the second one, we will get x2 is equal to 0 and x1 is equal to 2000. So we need to plot these 2 points in this xy plane. So for this is 0, 0 for both. This is the origin. Okay. Now x1 is equal to 0 is here, but x2 is equal to 1333. For example, I put this like it is 500, it is 1000, it is 1500. So it lies somewhere like there. This is the point. The first, this one. Now the second one will be here, like x1 is equal to 2000. So for example, it is 500, it is 1000, this is 1500, and this is 2000, this is 2500. And similarly, we get it like this. This is 2000 and this is 2500. Okay. So this is the point that we need to connect with this one. So we get this line. Now the direction of it will be, what will be the direction of this constraint? It will be towards the origin because it is less than or equal to 4000. Okay. Now we take the second constraint. The second constraint, it will give us 4x1 plus 2x2 less than or equal to 6000. So for this, x1 is equal to 0, x2 will be 3000. Okay. And for x2 is equal to 0, the x1 will be 6000 divided by 4, which gives us 1500. So now we have 2 points. The first one is 0 and 3000, and the second one is 1500 and 0. So the first point, x1 is equal to 0, we will write over here, and 3000 is somewhat over here. This is 3000. And x2 is equal to 0 is over here, and x1 is equal to 1500 is over here. So we will connect these 2 points. So now the solution of it, this space is infeasible. Why? Because it will contradict the first constraint. And this space is not feasible because it will contradict both of the constraints. This space is also not feasible because it will contradict the constraint 1. It is, the constraint 2. It is obeying points. We have plotted those 4 points on the xy plane. So the crosses that I did here, it means that these areas are in the not feasible region. So you cannot have solution in these areas. These are the not feasible solutions. Here, these areas, any point here is a feasible solution. But the optimal solution is where these 2 lines cross. So as there are only 2 constraints, you can have like 4 points. The first one is 0, 0. The second one is 0 and 1333. The third one is 1500 and 0. And the fourth one will be most probably, it will be somewhere like 400. Like 1350 and 400. So we have 4 actually, 0, 0, 0 and 1333, 1500 and 0. Other, it will be the most optimal. This is the optimal one where the 2 lines cross each other. And it is, I guess it will be somewhere 1350 for x1 and 400 for x2. So if we plot these 4 values in the objective function, we will get the maximum profit of 1350 plus 20 into 400. Which one? The My internet is good. I don't know if there is some problem with your internet. Yes, we have like 4 points. The first one is 0, 0. It is obvious from the XY plane that the first point is this one, the origin. This is not profitable. You have zero profits, but it is still feasible. The second point is when x1 is equal to 0 and the x2 is equal to 1333. So this is the point. The third point is where the x2 x2 is equal to 0, but x1 is 1500. This point. And the fourth one is where these two lines intersect. So this is the optimal solution. And this optimal solution, if we had like the proper graph plane, then we can, actually come to know that this is about 1350 and 400. X1 is equal to 1350 and x2 is equal to 400. So this is the optimal solution. When x1 is produced, the high phi 1 is produced in quantity of 1350 and the high phi 2 is produced 400 in quantity. And the profit that it will give us, the maximum profit it will give us will be like 1350 multiplied by 30 plus 20 into 400. It will give us $48,500 of profit. So this is the maximum profit that we can achieve. Now I will move towards a bit kind of, a bit complex from this problem. It will, it will also be like two variables, but it will have an additional thing that you will learn. Okay, because the question may be like tricky, so I want to learn some additional things too, so that you can tackle the questions in exam. So this is the question. You can mark it. It is 2.9, 29, 2-9, chapter 2, page number 78. Yes, it's Taha textbook. It is 29 and page 78 for your reference, that so that you can see it later on if you want to. So it says that the company produces two products, A and B. So from the problem definition, we come to know that there are two decision variables that we need to deal with, because we have two products, A and B. So it says that the sales volume of A, we have two products. The one is A, second one is B. Now the question says that the sales volume for A, it is at least 80% of the total sales of both A and B. So we represent A by X1 and product B by X2. And however, the company cannot sell more than 110 units of A. So this is again a constraint. Okay. And the sales volume for A is at least 80% of the total sales of both A and B. So this is again another constraint. So we have now two constraints over here. And the maximum daily availability for the raw material is 300 pounds. So this is the third constraint. The usage rate of raw material are 2 pounds per unit of A and 4 pounds per unit of B. So this is again another constraint. So we will have now like 5 constraints over here, 4 constraints. And the profits unit of A and B are $40.90 per unit of A and B. Determine the optimal product mix for the company. So we need to have the quantity of X1 and X2 combined so that the profits is maximum for the company. So as we have now seen that it has the profit in concern. So this is maximization problem. So the objective function will be maximum Z is equal to the A yields $40 in profit per unit, while B yields $90 in profit. So the objective function will be like this. Subject to, now we will come to the first constraint. The first constraint says that the sale volume of A, which is X1, is at least 80% of total sales of A and B. At least, it means that it is greater than or equal to 80%. So X1 is greater than or equal to 80% of X1 plus X2 combined. Now converting that 80% into decimal, it will give us 0.8 of X1 plus X2, or X1 is greater than or equal to 0.8 X1 plus 0.8 X2. You see? So this is the constraint 1. Now we will go to the second constraint. It says that the company cannot sell more than 110 units of A per day. So it means that X1 must be less than or equal to 110 units. This is the constraint, second constraint actually. Or C2. Okay. Now we will go to the third constraint of it. It says that both the products use one raw material, of which maximum daily availability is 300 pounds. And the usage rate of raw material is 2 pounds per unit of A and 4 pounds per unit for B. It means that 2 into X1 plus 4 into X2, 2 pounds per unit of A and 4 pounds per unit of B, and the total availability is it must be less than or equal to 300 pounds. So this is the third constraint. The fourth constraint is X1 and X2 must be greater than or equal to 0, which is non-negativity constraint. Non-negativity constraint. So this is how we, model the question, and we can easily solve it, for the using the graphical method. Should I solve it using graphical method, or this is okay? Okay, okay. I will solve it. The important thing is that you need to learn the how to model the question from a scenario, how to model it. If you can model it, you can easily then solve it. Okay. So for solution, we must simplify this thing, because this is where the question gets a little bit tricky. So simplifying it, we will get x1 is greater than or equal to 0.8 x1 plus 0.8 x2, implies that we will move the x1 into the x2 to the restrict x2 to the other side of the inequality. So it will become x1 minus 0.8 x1 0.8 x1 0.8 x2 0.2 x1 greater than or equal to 0.8 x1. So x1 greater than or equal to 0.8 divided by 0.2 into x2. So x1 greater than or equal to, it will give us so this is the final form of the constraint 2. You understand it how I did it? It's simple mathematics. Or should I do it again? Yes. So you get the final version as x1 greater than or equal to 4x2. So this is the constraint 1 now. Now we will move to the solution of the, so the final form is maximum z is equal to 40 x1 plus 90 x2, subject to, you should know that this is very important to write the mathematical model in this form, because if you do not write, you may be you may be deducted the marks by the professor. So this is the standard form. This is the standard form of it. Okay. So the first one is, this is the first constraint, greater than or equal to 4x2. The second one is that x1 must be less than or equal to 110 units. So this is the second one. And the third one is that 2x1 plus 4x2 less than or equal to 300 pounds. This is the raw material constraint, and x1, x2 greater than or equal to 0. Now we will solve it using graphical method. For the graphical method, we need to pick the first one and equate it. We can also equate it like that: x1 minus 4x2 is equal to 0. You understand the general mathematics of it? We make it equality, and then move both to a single side and equal it to 0. Or if you do not even equal it to 0, you can just write it in this form: x1 is equal to 4x2. And this is the way simpler than doing it in the second way. Now, putting x1 is equal to 0, we see that x2 is equal to 0 is equal to 4x2. It means that x2 is also is equal to 0. So the first point we get is 0, 0. Now, the second point. Putting x2 is equal to 0, we get x1 is also equal to 0. So second point is also 0, 0. So we get a plane, and both of the points are at 0, 0. So we do not need to plot it. Okay. Now moving on to the second one constraint, which says that x1 must be less than or equal to 110. So equate it: x1 is equal to 110. You do not need to, you know, compare it or put because there is no other variable. So we just put it. For example, this is 110 of x1. So this is the point. Now the third one. This is where you will do the other stuff. Now put x1 is equal to 0. We see that x2 is equal to 300 divided by 4, which gives us 75. Now putting this, we get x1 is equal to 0 and x2 is equal to 75. For example, this is 25, 50, and this is 75. So this is the point. Now putting x2 is equal to 0, we get x1 is equal to 150. So this is somewhere 150, and we connect these 2 points. So the solution is lying somewhere over here, and the optimal solution may be anywhere above this line. You see it? This is the optimal region, this one. Do you understand it? Now we can have like 4 points. Also, we will have 4 points over here. This one, this is the first point. Origin, this is the second point. This, the optimal region, this is the third point. And this one is the fourth point. We can get the coordinates of it and plot it into the maximum, the objective function, and we can have the optimal profit for this company. So what I will do is I will have these 4 points as follows. So 0, 0, 0 and 75, 110 and 0, and it will be somewhat 110 and 25 or 20 maybe. So putting all these, we get a maximum z is equal to 0 for this first one. For the second one, we get maximum z is equal to 0 plus 90 into 75. For the third one, we get maximum z is equal to 110 into 40 plus 0. And for the fourth one, we get 110 into 40 plus 20 into 90. So this one is the maximum. You understand it? Okay, I will go to the, my mobile phone is not charged properly. Yes, here we had instead of profit, you want to have cost. Okay, let me. Oh, fuck. uh, a manufacturer yes, anything? Okay, I am writing this is the problem number 249 and the page number is 86 in the same Taha book. Okay, so the problem says that the manufacturer produces three models, model 1, model 2, and model 3 of a certain product. So now we have three products over here. So the decision variables will be three in number. So though we cannot use the graphical method, but I will still, try to make a linear model of it so that you can understand the, somewhat complex problems. Okay. So it says that it has two raw materials. The raw materials are A and B. So I will say the raw material A and B. And these are the models of the products. So the model 1, we will represent with X1, the model 2, X2, and model 3 with X3. So these three are our variables here. Now we have two raw materials. Okay. So the model 1 will use 2 units of raw material of A. The model 2 will use 3 units of 3 pounds of raw material A, and the model 3 will use 5 pounds. And the total availability, the maximum availability for the raw material A is 4,000, and for the raw material B it is 6,000, while it is used as 4, 2, and 7 respectively in product A, B, and C. Now there is another constraint, which is the minimum demand. Remember that it is minimum demand, not maximum demand. For X1 is 200 units. For X2 it is also 200 units, and for X3 it is 150 units. And the price. Now here we have price as an option in scope that we need to focus on. So whenever there comes price, it means it is related to cost. So we will try to minimize it. So this is a minimization problem. So these are the prices or cost per unit of X1, X2, and X3 respectively. So this will be which problem? Hello? So this will be the minimization problem. So we will write it as minimize Z 30x1 plus 20x2 plus 50 into x3. So this is a minimization problem. Subject to, okay, first of all, we will take the constraint for raw material A, which says that the raw material A is used 2 pounds in X1, 3 pounds in X2, and 5 pounds in X3, while the total availability must be less than or equal to 4,000. So this is constraint 1 for raw material A. Now for raw material B, we have it is used like 4 pounds in X1 plus 2 pounds in X2 plus 7 pounds in X3, and the total availability must be less than or equal to 6,000. So this is constraint 2. Now we have the constraint for minimum demand also, which says that the minimum demand for x1 is 200. It means that x1 can be greater than or equal to 200 because 200 is the minimum demand. The minimum demand for x2 is also 200. So x2 must be greater than or equal to 200. And x3 is minimum demand is 150. So x3 must be greater than or equal to 150. So these are the constraints, and the other one will be x1, x2, x3 greater than or equal to 0, which is non-negativity constraint. So this is how we make model for a somewhat complex. Now you understand it. So this is how the yes, same procedure, but now we have three variables, so we cannot draw it on paper like x, y, and z. We cannot make z plane on a paper, so we cannot do it using the graphical method. Inshallah, in the next lecture, we will entertain such problems with three or four or five variables, and will use the simplex method. And also, after simplex method on hand, we will also try the Torah, and we will compare both the results for the same question. So till then, I will download Torah. If you have Torah, a copy of Torah, kindly, you can email it to Josefa, and he can give it to me. Okay. So this is how the modeling part is done. Inshallah, in the next lecture, we will do the simplex method, and we'll go for Torah. And inshallah, after that, we will go for the network model and the other things that you are studying. But please also send me the course content of your subject, so that I also follow the same track as your instructor. Yes, yes. So yes, you can send me the notes or sensitivity analysis. Yes, yes. So that is, I guess, in chapter 4 or something, sensitivity analysis, or chapter 3 maybe. It is related to simplex, because when you solve it by Torah, it also gives you the sensitivity, analysis of it. Or using Excel, it automatically gives you sensitivity analysis. It is also called the dual problems. So we will cover it, inshallah, in the next upcoming lectures. Yes, yes, inshallah, we will cover it in the upcoming lecture. But for the yes, inshallah, inshallah. So I hope you have understand. Thank you. Welcome. You welcome. Okay, I guess it is all for today, and I hope we can carry on with the same zeal and energy. Inshallah, inshallah. Okay, so that's all for today. Take care, and when when is your exam coming? Josefa told me that you have an exam also on some 20th. Okay, so okay, so you should also send the teacher must have given you some modules to study for the exams, at these chapters or something like that, these are coming in the exam. So also please tell Josefa that these chapters are for the exam, so that we can explain it using problems from those chapters, and to get the good grade. Yes, so